Welcome back to an Introduction to Engineering Mechanics. This is Module 9. We're going to learn how to use Vergnon's theorem to sum moments today, and we're going to solve a two-dimensional moment problem. First of all, let's look at the definition of the moment, and I've changed it a little bit this time. Last time we said moment about point P. It can be a moment about any point, so I've just changed the notation to kind of get you used to doing different notations. So I have the sum of the moment about A is equal to R from A to B, where B is a point along the line of action of the force crossed with the force itself. Now, Vergnon's theorem says, it's also called the principle of moments, that we can take the moment of a force is equal to the algebraic sum of the components of that force. And so if I have a force F that I can break into two components, F1 and F2, then R cross F is the same as R cross F1 plus R cross F2. And we'll use that in solving the 2D problem today. So let's look at a vector solution of a problem. Let's take this demonstration over here. I have a section of an I-beam, and I'm going to pull down and to the right on a 3-on-4 slope with a 20-pound force, and I want to see what the moment is, the tendency to cause a rotation about point O is here in the center of the I-beam. And so that's the setup of the problem. Okay, let's use the vector method for finding this moment. So we have the moment about point O is equal to the position vector from the point about which we're rotating, O, to a point on the line of action of the force. And the most readily available point on the line of action of the force that we know is point A. So we'll go from O to A, and then cross it with the force vector itself. And so ROA, you should be able to easily find on your own. Once you do that, you'll see that ROA is 2 units, 2 inches in the I direction and 3 inches in the J direction. So this is 2I plus 3J. To find the force vector, we first need to find, we know its magnitude, we need to find its direction. And so we have a position vector along the line of action of the force, AF we'll call it, goes 4 units in the I direction and minus 3 units in the J direction. So AF is equal to 4I minus 3J. That means that the magnitude of AF is equal to the square root of the sum of the squares, or 5. So the magnitude of AF equals 5. And therefore, a unit vector in the direction of the force is equal to position vector AF divided by its magnitude, or in this case, 4 divided by 5 is 0.8 in the I direction, and then 3 divided by 5 is minus 0.6 in the J direction. And so that allows us to write the force as in vector form with a magnitude and its direction. Its magnitude is 20. Its direction is 0.8 in the I direction minus 0.6 in the J direction. And so that's 16I minus 12J. And the force units are pounds in this case. The position vector units are up here are inches. And so now I have ROA, I have F. I can substitute it in and do the cross product to find the moment about point O. The moment about point O is then ROA cross F, or 2I plus 3J crossed with 16I minus 12J. And if you do that cross product, you'll get minus 72 in the K direction, and the units are, the position vector is inches, the force is pounds, so this is inch pounds in the negative K direction. If I want to just draw it with an arrow, the negative K direction is back in this direction, so that means you have a clockwise rotation of my I-beam, which makes physical sense. So I could also write this as 72 inch-pounds, and the direction is clockwise. Excuse me, That's right, I wrote it wrong. It should be clockwise, so it should be the other direction. Clockwise, in the minus k direction. Okay, so that's the vector method. Okay, let's redo this problem using the scalar method. And we saw that by definition, the magnitude of the moment about point O is equal to the magnitude of the force F times the perpendicular distance to the force F. And so you'll see here that the line of action of this force, to find the perpendicular distance to that line of action would be geometrically difficult. And so what we're going to do is we're going to take advantage, again, of Varignon's theorem, and we're going to split this force into its x and y components. And so we've got f of x and f of y. And then we know that this is equal to f sub x times d perpendicular to the x force plus f of y times d perpendicular to the y force. And in summing these moments, we're going to have a sign convention for the direction that these moments are acting. And so I'll go ahead and arbitrarily choose clockwise as positive. And so we've got the moment, and I should have a moment, a vector symbol there. So I got the magnitude of the moment about O is equal to f of x. Well, the magnitude of f of x by similar triangles is corresponds to the 4/5 component of f, or 4/5 times 20. And then we have to find the perpendicular distance from the line of action of the f sub x force to the point about which we're rotating. And so here's the line of action of the force f sub x. And here's the perpendicular distance, 2.0. And so we see that that is equal to 3 inches. And so we've got 4/5 20 times that perpendicular distance, which is 3 inches. And it's going to be positive because that f of x causes a clockwise rotation about point O, and that's positive in accordance with my sign convention. Now I have f sub y by similar triangles. It's the 3/5 side. It's also going to cause a clockwise rotation, so it's going to be positive according to my sign convention. And like we saw in an earlier module, you could arbitrarily choose an opposite direction and you'd get the same answer for your sign convention. And so we've got plus 3/5 of 20, and we've got to find that perpendicular distance. And so here's the line of action of the force f sub y. And so its perpendicular distance, the perpendicular distance from O to that line of action of that force, is d perpendicular y equals 2 inches. This is times 2. And if I multiply those out, I get 72. Since it's positive, it means that the moment is going to be clockwise. So I have the moment about point O as a vector is going to be 72. Units are inch pounds, and the direction is clockwise. I can also put that in vector form. Here's my x-axis, here's my y-axis. If I go clockwise, by the right-hand rule, that's into the board, so that's the negative k direction, so that's equal to minus 72k inch pounds. And so that's the exact same answer that we've got using the vector method. And that's the end of today's module. See you next time.